In university.
Yes.
Guillaume, are you ready to share?
We have.
I don't think I'm the chair for this session.
I like
Never know where to stand.
All right, people, let's listen to Andrés talking to us about decomposite. Zoom thing is in the way.
All right. Yeah, good morning. Thanks for still being here after this very long week. These weeks are fun, but they do become long after.
Currently live and safe.
I'm glad you're live and safe. It's that means you're the whole thing. But, the okay, I'll say that later. Sorry. So right. So just to recap, we've been seeing label transition systems, what they are, how we can use them to model protocols of different kinds, and how we can use temporal logic to describe them. Specifically, linear temporal logic is what we saw yesterday. And the types of properties that linear temporal logic can talk about are these linear time properties, which are just infinite sequences, because remember, we are assuming that all traces are infinite, so we don't have states that stop where there's no outgoing transition. So we have these infinite traces of atomic propositions, and these are linear time properties because they refer to things happening one after the other. So I cannot consider multiple options in the future at once, in a sense. I can consider multiple behaviors in a property, but the properties are linear. So we've been trying to understand how these properties look like, and we looked at the different categories of them, and particularly we looked at what safety properties are and liveness properties, and we saw that safety properties are the properties that constrain the finite behavior, right? So there's no bad prefix. There's not like, if something's bad's going to happen, like some unsafe behavior, we can see it in finite time. So these are the safety properties. And on the other hand, liveness properties, they constrain the infinite behavior. They say, well, these kind of things happen infinitely often, for example. Right? So the green light comes infinitely often. And so I ended with this nice decomposition theorem or property. I think it's nice. It gives us some sort of piece of it can give us some sort of peace of mind that, well, we cover the space of possible linear properties if we can cover safety and liveness, in the sense that we can. So I said, if I have a linear time property P over some set of atomic propositions AP, then there's a liveness property P live and a safety property P safe that decompose the property between the two. So P live cap, I always forget, intersection P live and P safe is the property P. So I'm gonna try and sketch a proof of this, just to give you an intuition about how you can do this. But this is very much just a sketch, and I'm gonna omit like the juicy details, but this gives you kind of the idea of why this kind of thing can work. So the key intuition is that we can make this set of infinite sequences over the power set of atomic propositions. We can make this into a metric space by defining a metric on them, well, unsurprisingly. So if we have two sequences that are equal, then the metric, we define it to be 0. And if not, we take the greatest common prefix between the two. So we see basically how far can I go until they differ, and then I just divide that. So I think we're taking 1 over n, where n is the length of this greatest common prefix. And if you think about it for a few minutes, you can convince yourself that this actually makes this into a metric space. Like the interesting thing would be the triangle inequality here, but if you just work it out, that should work. And so once we have this as a metric space, well, metric spaces induce topology, so we can look at the topology that you get from that. And I'm not going to prove why, but if you think about it, the closed sets of the topology that comes about by this are exactly the liveness properties. So if you remember, liveness properties are those where the finite behavior doesn't matter, right? So if you think about it, the finite behavior doesn't matter. So if you think in real intuition, which might not be a great idea for topology, but maybe for metric spaces, right? If I'm going over the limit of something, like that means the two traces are the same even farther and farther ahead. So the finite behavior of them agrees, and it's just about the infinite behavior. So the closed sets are those that where I can always extend them like this. So I can always take a finite prefix and extend it. So if that doesn't make much sense, don't worry, but I'm just trying to give an intuition why these are the closed sets. And so then this basically follows from topology. Like I can just take the closure of P and say that's a safety property because they're the closed sets. And then this is just some set theory, right? So this is basically the complement of this. And if I take P and its complement, that's the whole thing. And then I can, yeah.
So P closure should be live though, right? Because you said liveness with the closed set. So if you take the closure, it should be the liveness property, right?
Did I mess those up? Yeah. P close is alive. Yeah, I think just to those two. Sorry. This is maybe I shouldn't. This is just getting me to blame myself more by looking and making a proof in the.
Why is the
And why is the other one a safety property?
Yeah, so it's basically, yeah, I haven't said it. The key idea is that this is a dense set in this topology, and you can decompose no wait. So it's a dense and a closed set, yeah. So I think this has to be a. So I think you can. I don't. You have to do some algebraic manipulation to show that this is dense, and because it's dense. If you think about it again, the dense sets are the live. The safeties, yeah. I'm just going off. Let me see. Yeah, the safety properties are the dense sets, and it's exactly the other way around. Like this metric basically distinguishes between things that are where the finite behavior and the infinite behavior matters. Let's not dwell on this. This is this is very sketchy. So I'll just move on from that. So well, that's been kind of. I just wanted to talk about that characterization thing, but because it's the last day, maybe we can just look at some more examples. I don't want to show more. Basically, I don't want to show more theory or more of the concepts. I just want to show some examples. So I'm gonna show some examples about here in paper how we can look at some properties, but then maybe we can play around. I can show examples in spin. We can play with spin with some of the examples that I've shown here. So first, I just want to talk about deadlock checking. We mentioned this yesterday, but basically, if you want to check for a deadlock if you remember, checking for deadlocks means there's no end states that don't have any outgoing transitions. So when we're doing this transformation to ensure that there's none of these states, we're already checking for deadlocks. So checking for deadlocks is kind of a pre-processing step. And in spin, what you do is if you don't label a state with end and it reaches it and it cannot go out of it, it'll automatically tell you it's an invalid end state, so it's a deadlock. Because it's doing this transformation implicitly. So there's an old way of translating any LTL formula into a never claim, which is kind of the what spin started with. You can now also specify LTL formula. So I can so spin. This is just from the manual. And actually, I'm gonna show this. So there's these two examples. Better. I had them here just as screenshots, but it's nicer if we look at them in practice. So before we look at the examples, I just wanted to have one small word on complexity. I'm not. Yeah. So just to talk a little bit about how difficult is this problem and how complicated is it to solve. The thing is, checking an LTL property and one of these LTSs, if the LTS is finite, it's the complexity basically depends on the property. That's the key intuition. That's also the reason why we've been being also more refined about what kind of properties we consider, because different types of properties are differently easy. So invariants are nice because invariants. So if you remember, invariants are the properties of the form always P, where P is some propositional property. So in the propositional fragment. So invariants basically are not saying something about the dynamics of the system. They're not saying something about time behavior. They're saying something about the state, right? And so checking an invariant is just, if you think about it in the state graph, it's just a reachability analysis. Can I reach a state in that state graph?
Is it correct to say that an invariant is any LTL property that doesn't use the diamond?
No, because it does use the time. It's always something.
No, but you want
So you want this to always hold. If it's
exactly. So it's a box, right?
a box, yeah, that's the time.
Okay, so let's rephrase that. Is an invariant anything prefixed to the box?
Yes,
But you
it's
can still
anything
use
prefixed to the
diamonds.
box, and then the rest is in the LTL front, in the propositional front. Yes.
So you can still use diamonds after the box. then?
No,
No. Okay, so it's only diamond and then a
it's only box
Propositional
and a
state.
propositional, and something in the propositional. front.
okay, so something that holds from start up until
Exactly.
infinitum.
Yeah. And that's why it's called an invariant, because it doesn't
It
change.
should always.
Yeah. So it is in a sense a time property, because you're saying this holds the whole time and not just at some particular point. But it is it's a special type of type property that you can that only depends on the state. That's the critical thing. It just depends on the state. It doesn't depend on how you got to that state.
Okay.
Yeah.
So I thought I knew what an invariant was,
Mhm.
but now perhaps I don't. So consider the expression once a crook, always a crook,
Right.
okay? Sorry for the negative example.
That's-
But what that says is box if you commit a crime if you're a crook today, then you're a crook tomorrow.
So I'd interpret once a crook, always a crook as wouldn't that be an eventually, right?
I would say it's a diamond
Yeah,
and box. So there is a time when I wasn't a crook. Eventually I become a crook. But once I do,
So diamond crook implies box.
yeah, that's how I would interpret it.
Yeah.
Diamond crook implies,
so there's a point in time that once you become a crook,
Then you're always a
then
crook
you're
after
always
that.
a crook.
But it's not an invariant.
But it's not an invariant.
So that's not an invariant in your.
that would not be an invariant the way I defined invariant to be. I mean, I can show it back. So. It's box P where P is proposition.
Doesn't mention time.
It's only mentions time in the first box.
Thank you. P
Doesn't mention time.
Yes.
Yeah.
Thank you very much.
Yeah. How do you? We can talk about maybe we can model the crook one also in spin. So checking invariants the way I define them as box and some proposition, some proposition in the propositional fragment. That's it. I don't know how to say this non-redundantly. That's just so what you do is breadth first search in the state graph, but it's just basically a reachability analysis. And in that sense, it's linear in both in all three: the state space S, the formula, the length of the formula phi, and the number of transitions in the state space. That's usually still quite large, right? Like S is usually huge for these systems, but it's not like this is absolutely very easy, but if you like complexity theory, it's linear in that sense. So that's good. And general LTL model checking for this kind of systems is P space hard. I'm not going to explain why, but because I don't understand complexity theory that well. But I think this is also a relatively well-known example. I don't remember how you do the translation to a different P space hard problem. But in practice, if you want to use this to verify something, there's a lot of mitigations that you can do. I'm going to talk about a few of them here, just at a high level. But yeah, maybe if we do this course again sometime, maybe I should talk more about the mitigations in practice. That's nice, but at least I can give you an idea of them. So there's two things that model checkers do often on their own. One of them is called partial order reduction. Kind of the idea of partial order reduction is dynamically saying, okay, if I've already seen a state, so I keep kind of a hash of the states I've seen, or I keep track of the states I've seen. So there might be multiple paths leading to the same state. I don't want to check on the multiple paths going forward. So if I reach a state, I can move on for that. This doesn't always work because sometimes the formula depends on the past, right? So if the formula depends on the past, right? So if the formula depends on how I got there, I cannot do partial order reduction.
So as far as I know, isn't partial order reduction rather about like keeping track of transitions? Like it can be used in stateless model checking as well, without keeping track of states.
Well, I think so. I think there's a sense in which the two are dual in the sense that they're you can take a model that has the labels on the states and put the labels on the transitions and vice versa. Maybe what you're saying is in that formulation. But so in this case, we're not keeping track of the transitions. We don't have labels on the transitions. All the atomic propositions are defined on states. So we cannot meaningfully talk about anything about the transitions in this formulation. But I think So I think what you're saying is the same, just if you put the labels on the transition. Symmetry reduction. Basically, if you think again of this as a graph, like the state graph, that graph has a group of automorphisms, meaning there are transformations that take the graph to itself. And so if I check on one path and there's a symmetric path on the other side of the graph, I just have to check one of the two. And usually these, so Promela has external tools that it can use to do that, but other model checkers have built-in primitives that let you build things in a symmetric way. Much more interesting from the modeling perspective, because there you can do things, is abstraction. So we haven't defined abstraction, but you can think of this in the, and we also haven't defined refinements, but you can think of this in the usual way you think of it in other things. So an abstraction, if you have two, so you can define some sort of mappings between transition systems that preserves. So you can think of the trace that. So if you remember the trace equivalence we had, we can define that also, like only on one side traces are a subset of the traces of the other, and you can also define this on the states, like some stronger notions of this, like simulation relations, and then the one that goes back and forth by simulation relations. So with all these notions of equivalence, you can also show that if a property holds on one state, it also holds on one transition system, it also holds on a different transition system. And if you have that kind of mapping, you can take the smaller transition system and prove your properties there, and you know that that's a sound abstraction for the other one. So you can that also, so that the mapping plus the property on the small system proves the property on the big system. That's kind of the idea of abstraction. And usually you want to do like towers of these refinements so that you can prove your property. What we've been talking about right now, all the states are concrete values, but you can also treat them symbolically, and there's a whole subfield of symbolic model checking. It's not strictly better, it's different, it depends on the kind of state space. So if your state space, like the transitions depend a lot on the actual values, then this is not as useful. But if you have very large state spaces where a lot of things are the same because you can reason symbolically, then symbolic checking, model checking is quite nice. So that's another good tool in toolbox. And there's more things, but these are the kind of more interesting ways of actually dealing with larger state spaces, larger models that you usually have to go back to in practice. So that's the end of the slide set. But I skipped these two because I want to show that on Promela. So maybe we can just play around with Promela. And I also have a nicer, like a bigger example we could look at if you want. So I'm not a big fan of VS Code, but it's the only one that has syntax silencing for Promela. So let's not look at this first. So here's the hello Promela example we had before. Yeah, so is that better? No, what are you doing? And so I can also make this bigger. Does that work like that? So I can say spin, just run a Promela examples, Promela. Okay, maybe we don't want to run, we just want to simulate it. And then it says, so if you say run, it's going to run the model checker. If you, so dash run, if you just run it like this, it's going to simulate it. So it's going to do a random version of the two. In this case, this is completely deterministic. So there's nothing very interesting going on. But we can look at these traffic light examples, right? So this is the example we had before. We've seen it. So you have the these transitions. This is the version that's just one big transition system. And so here's this. Here's where it becomes interesting, where you can specify LTL properties. So there's this LTL keyword, and I can give it a name. So I'm just calling it warning, and then this is the way you write box. So it's saying box car not equals yellow implies next car is not red. If you remember that, that's what we're saying. Like, if you're not, you want yellow to be preceded by red, but we cannot talk about the past in this logic. So we're talking about it kind of in this way about the future. So unless you're yellow now, I don't want you to be red in the next state. And so we can run this iSpin, which is a very nice TCL interface from probably older than many of us here. I don't know, maybe it's not older than me, but definitely older than a few people in the audience, I'm sure. But it works. So we can fire up this example here. It was bottom right. Thanks. I don't know if I can increase the font here, but this is just the code that we saw just before. So here you have like these tabs, and you can go to verification, and you can just run it, and it's gonna run it, say, okay, there was 9 states, 11 transitions, nothing happened. But actually, it's kind of annoying. It didn't actually check our property. We have to actually tell it to use the claim. Because there's just one claim, it's gonna use that one, but I can also write warning because I named it the property warning, and tell it to run. And then it's run, it says search not completed, never claim warning, and there's assertion violations plus, so something went wrong. So there's a problem, this doesn't hold. And then we can look at why. So there's this simulate replay thing. It writes down a trace. So if you look at it here, it's got these .trail files here. So traffic light basic.trail, and that's just recorded the sequence of steps. So now we can replay that. And okay, so this, I think this trail is empty, is that? Why?
Is there some on the left explaining the situation?
No, oh yeah, so this is, but normally you can see here the sequence of steps.
So it's step 12, no? It's highlighted in orange.
It's highlighted in orange.
So here,
I think the center console.
yes, the center console. So,
Yeah, but so don't worry. Normally there's like a little
oh,
trace here. I think this trace is just too small and it doesn't show it, but basically because you can see here the state. So you can see car is equal to red and walk is equal to green. So what happened? The pedestrian traffic light changed, and so the traffic light, the car traffic light did not change. So our condition was not the right condition in this case. It's also not the one that we had in the slides. So I purposely put here the wrong version that you could intuitively think. So okay, you don't want to go to red unless it's yellow, but of course it could already be in red and something else happened somewhere else. So we kind of want to say car is not equal to yellow or car is not equal to red. So you kind of want to be able to stay here. You have to reopen this so that it reloads it. happens with all these old systems. You don't have a proper editor, so you have to reload it like this or Isabel or stuff like that. Sorry, I have to make that one. And now it runs and it says, yeah, thanks. So it actually still says it didn't find one. So you guys spotted the mistake before I did. Thanks. So it's keeping us honest. Reopen. And now we can run it. And now it says no errors found. Did you verify all claims? So this property holds. Great. So that's kind of the idea of how Promela works. We can maybe look at, maybe I want to show another example before we look at the big example from practice. So if you remember this I have here a little bit of ASCII art explaining what this one does. Or you can look at it here because it's going to be easier to read. So we did look at this on one of the on one of the lectures before. So we have these two endpoints, endpoint 1 and endpoint 2, and they're connected by a network with buffers and routers, and they're just sending messages to each other, and they're doing it atomically, right? So if you remember, like we're checking, okay, is there something in the buffer? Then we can send it so that it doesn't block. And then we can run this example to see. So in this case, I don't have specified any property, because what I care about is deadlocks for this case. I want this network not to deadlock. But if I want to not to deadlock, like I said, it's kind of like this pre-processing step. So it just, by just pre-processing it, it'll tell me if there was a deadlock on it or not. So let's just run it. And so it runs it here. Now it's at so also, by the way, if you see, it's actually building this pan.c and compiling it and running it. So it's actually compiling this C file. And now it says invalid end state at depth 7,985. So it does deadlock after 7,985 steps. I'm absolutely sure that's not a minimal file, like trace of a deadlock, but it found one. So we can again use this simulating trail. And if I start doing it here, you can see that's what I was missing last time because the trace was too small. And this takes forever. So I can actually start here. Let's say skip the first 7,000 steps. And now it's just going to run the few ones that we're missing. So you can see here kind of maybe that was still right. The model checking goes very fast, but you're like drawing all these little boxes on the Tickle interface, I guess takes a bit longer. How many was that? 7,000?
It's getting close.
Oh, yeah, there you go. Okay, cool. So you can kind of try and make sense of these things. Like, so here you can see process 1 is reading a request, and then it's reading the request from above here, where no, I guess so. I don't know what. Let's look at this, right? So 1 sends a request, and 4 reads from request. So this is kind of like a visualization of the things that happened. Normally, for easy things, it's easier to look at what the state is and so this is the state of the individual processes, and these here are the queues, right? So if you remember, we had these channels, and the channels have some finite capacity, and it actually kind of. So I'm sorry if this is hard to read because I don't know how to increase the size. I don't know if Tickle can do that, but I can read it kind of out loud here. So you see here you have it says router 4, buffer 2, and then it's showing the state, request. This got response, request. And here so everything is full. So here all the endpoints also have, so here these two have requests that they want to respond to, and these two routers are passing something along a response and a request. So if you think about what happened is like everybody starts sending. If everybody starts sending and the network gets too full, because sometimes you have a dependency. When you get a request, you want to send a response, then that'll block the network and everything's full. So these two endpoints have received both a request, want to send a response, but cannot send the response further because the buffers are full. And these buffers, to be empty, they have to actually send the responses. So these responses that are here in flight, they have to arrive at the endpoints and be processed. So if the buffers were bigger, everything could be processed and everything's fine. But if everything gets full, then we deadlock. I think it's not terribly intuitive, actually. It's like once you see the example, you can figure that out. But yeah.
From the counter example being so long, I guess it's not a breadth first search. So what kind of techniques are implemented in spin, or what's used right here?
So I honestly don't know what kind of technique they're using. I don't know if that I think that could be breadth first search, actually. Like I don't understand your argument. Why wouldn't it be breadth first? Depth first search would find it faster, right? But breadth first,
I mean, breadth first seems like finding the shortest.
maybe.
Not fast,
It's
but-
probably got some heuristics inside. So okay, I see your point. Yeah, maybe so depth first would be faster to find the counterexample, but the counterexample would be longer, and breadth would be find the smallest. I don't know. Maybe you can actually change also the strategy in which it runs it.
They're right, there's breadth first search, a checkbox, third column.
And
Oh, yes, state 36.
Yeah, it's much smaller.
you guys are much faster to see this here. Okay, yeah, 36. Oh, cool. See you found it out, and it's kind of the same now. It's just going more direct. Great, thanks for that question. That was good to know. So you can we could kind of add something else. Yeah, it's a shame I didn't keep the version of that. I might just copy it over. So you can have this. I kind of cheated. I had something else, the example somewhere else before. So what you can so you can add this thing that's called flow control. And what flow control does is it says, well, if the network is too busy, don't send things. So we have this, now we have this different, instead of just sending a new request whenever we want, we have this question before. So we say, okay, does the buffer that I'm going to send something still have space? And it's kind of checking, well, if it's, so either it has space, and I'm not processing a request at the same time. So this message equals nil. If you remember, this is kind of what I just received before. Am I still processing a request that I have to respond to? Or just consume a response? And this is also checking, I don't want to have two requests at the same time. In fact, that's just a policy for flow control, so that things don't go off so quickly. And if we reopen this and run it, now it takes a bit longer. Now it just took 0.29 seconds. No errors found. Did you verify claims? So there's no deadlock. But we can see actually the state space is quite big. So that's 400,000 states. So this state space can explode quite quickly. And it's I find it impressive that it can explore 400,000 states in 0.29 seconds. So that's pretty cool. So as a final thing, I'm going to show you one example. So these are all toy examples. I'm going to show you a non-toy example with a little anecdote. So this is just for the context. So this was some work we were doing on memory models. So memory models tell you how, and OpenOffice screwed that up. So
It's the exchange button I lets you swap the screens.
oh, what?
No, on your computer.
Oh, okay. That's not even what it's just. Maybe.
It's fine. Anyway.
It doesn't matter. It's just to give you a little bit of context.
Oh, maybe if you press the slides.
Yeah.
button, Right next to the timer? No, it's, oh, okay.
Maybe if it press this, no.
Oh, wow.
Okay, sorry, doesn't matter. So what's a memory model? Just to give you a context so that I don't show you some code and you have no idea what it means. So memory models kind of tell you. So we've been thinking about we've been looking at these interleavings, right? So if you think of the semantics of processes when they interleave together, one goes first, the other one goes after. We even define these semantics here. And usually when you think about concurrency, that's the way you try to reason about concurrency of things not interacting. But shared memory systems actually don't implement this. This is kind of because the hardware manufacturers want to optimize things, they sometimes will reorder the events in the order in which events appear to occur. So even if your processor wants to execute these in this order, the execution might appear in a different order because either the pipeline executes them out of order or the cache coherency protocols serializes things out of order, etc. So the reality is that this thing here that's called sequential consistency is basically not the case in any piece of modern hardware, really. So you have different memory models depending on your hardware architecture. So x86 processors are relatively strong, so they don't admit that many reordering, but they do admit some that would not be allowed by sequential consistency. And there's other architectures like ARM that allow more reorderings. That's all you need to know about memory models for understanding this example. And we have this operational semantics to define to model some sort of memory models. The idea is you have kind of these accesses. So if you want to reason about what this program is doing, it reads, it writes to this value, it reads this value, and then you have the two threads here, and things propagate. So this writes propagate to a different thread, and then we keep track of some dependencies. The reads propagate to a different thread, and then you can satisfy the reads if they match. I just want to give you the high-level intuition. I'm not trying to go into the details of that. So, and in this way, you can model the behavior of more complicated systems. So this was originally a model for an ARM architecture operationally, actually, I don't want to go into too much detail of that, basically, but maybe I should have skipped it. But I want to show you this example here, because this is the example that I want to show you the code for. So this is some really complicated. These are called litmus tests, and this is some really weird behavior that you can see on some architectures. So I want to show the. Actually, well, it's the same. Yeah, let's just look at it here. So we have 4 threads, and one writes to a variable x, and the other one writes to a variable y. And we assume at the beginning x and y are initialized to 0. And so we read the other 2 threads read those 2 variables, but in opposing orders. X equals y, something reads x and y, and this one reads y and x. And so some processors actually show the behavior that this one reads 1, 0, and this one also reads 1, 0. So in some sense, this write here just happens locally in this side of the processor, and this right here just happens in this side of the processor, and there's no global ordering in which all things happen. This is weird. It's called IRIW, independent reads of independent writes, and it's a way to check a property called non-multi-copy atomicity. If those words don't mean anything to you, don't worry. It's just we want to model this behavior that can happen in actual systems. And I'll tell you, so there's a little anecdote that comes with this. So I actually defined this operational semantics in the functional programming or peer improver language of my choice, and wrote a little decision procedure for it and let that run on this example with the 4 threads. I forgot about it. It was running in the background. It ran for a month and it didn't finish. So after that, we used other ways of dealing with this. We do it manually. It was kind of complicated. But then I thought, why don't I just model check this? So that's what I did here. And so this is the litmus test that we had before. And here, because I was, after having this having been a month, running for a month and then working, I was like, I want this to be very, run very fast. I want to do this very optimized. So you'll have to excuse that this is kind of hard to read. The state is just this byte, and I'm encoding this vector of 6 bytes. I should have used nicer number names, but I'm just trying to say, okay, the bits 0 to 3 are telling me if it's propagated to threads 0 to 3, and the index of this index is telling me which request. So if I request, so this is basically saying, so these are the bits in each byte, and so there's 6 requests in this litmus test here, right? And they're orders 0, 1, 2, 3, 4, 5, and so the index here, because the people that wrote this don't know how to count, I have to also not count properly. But I'm encoding it kind of in this way, and these, if you remember, there's these lines that showed if 2 things depend on each other. I'm encoding this as well here. The index is which request, and so basically the relation request prime is encoded here by the index and the bits. So and it's because it's 6 requests, it fits in a byte. Right. And so this is kind of manually encoding the semantics of this with this bit vector assertions. Here, we're not going to look at them, but basically I have 1 proc for every thread. And this is also kind of, so in hindsight, this was all overkill, and you'll see why, but I'm kind of also So this is not an LTL formula because I don't know if I think I didn't know that I could write the LTL formulas nicely with that syntax at this point. So it's using this never thing, which basically never is just not like always not. And we're checking that these things. So this is kind of preemptively checking as soon as we know. So this is, yeah. I'm not checking if the behavior actually happened, but I'm checking a condition from which I know that this behavior will certainly happen. And so it's kind of preemptively checking them. We're not going to look into exactly how that is, but remember this run on a month on my naive implementation. And it was absolutely not as tightly compacted here. But then when I run this here, it's running. Now it takes a little bit longer. And it's done in 4 seconds. And so here you can also see how it's kind of telling you how it's progressing in the number of the memory it's using, etc. So it checked a bit less than 8 million states in a bit over 4 seconds, and it didn't find any violations of the never claim. So it means this behavior cannot happen in this case. So it's basically proving. So when the behavior happens, it's easy. You just find a counter, like you just find a trace, a violating trace, and that I could do with my homegrown implementation. It take longer, but it worked well. But when the property holds like this, then you actually have to search the entire search space, right? So I thought it's impressive that it can check almost 8 million states in 4 seconds. So that's kind of just an example from practice. There's a question here.
Yeah, I think there are tools that can support now, like memory consistency models. And then you don't have to do that like manually, which is like tedious even for a small example like this.
Yeah, you're right. There are, I'm aware of them. Most of the tools support. So just for context, this was, we're trying to model consistency models when you have 2 different architectures on one system, which is something that's kind of starting to happen. Most of the tools that do that, so if you think of the AY7, for example, that's like the most prominent one, but you can also use a different tool, which I forget the name from this guy at MIT, but it's actually not, it's like some relational algebra, and it's translated to SMT. So it's not specific for this, but the point I'm trying to make is all of these tools work on a declarative style of memory model semantics, which people like to call axiomatic semantics, and that's not well suited for composing systems. So we try to do it with that way. If you have a way of composing axiomatic models of memory models, that'd be great. I'd love to hear it. I think that would be a really cool thing. But we didn't know operational semantics are easier for architects. So I was collaborating with some architects here. They kind of understand what's happening in the operational semantics. If I start showing them this, oh, there's a cycle here in the RF-FR PPO relation, then like I don't understand what's happening there. But they're nicer because they're like their computational behavior is nicer than this operational models, but I don't know how to compose them. So yeah, that's what I mean.
Someone probably already did the axiomatic system for like the main architectures, and then you can just reuse it. Or is there no available axiomatic system for like R more?
There is, but this was so what I was trying to model here is TSO, which is x86, plus PTX, which is the NVIDIA memory model, because people are putting memory consistency, like cache coherent systems where you have shared memory between the CPU and the GPU. And there's no memory model for that. Well, there is our LDI paper from last year, but there is, I'm not aware of another memory model for that. I'm not aware of how you do this axiomatically. Like for systems that have this behavior, this is called non-multi-copy atomicity, which is kind of weird, more difficult to handle in some sense. Yeah. Okay. Yeah. Thanks. Playing around with Promela paid off that we can see some things in practice, and we also actually had enough to do for this last hour. So thanks. I'm happy that you stayed up until the end. Oh yeah, I think that this is the end of the time, right? Yeah.